The history of Euler's number. Although commonly associated with Leonhard Euler, the constant E was first discovered in 1683 by the mathematician Jacob Bernoulli. He was trying to determine how wealth would grow if interest were compounded more often than on an annual basis. Imagine you are lending money to a bank that applies a 100% interest rate compounded once a year. From tutorial 5.4, we know that compound interest is calculated together with the principal P, i.e. by calculating the total amount A, through the compound interest formula. We have the following shown on screen, where n is the number of times the interest is compounded in a year and r is the compound interest rate expressed as a decimal. Give the above conditions: n equals 1, r equals 100% equals 1, and n equals 1. After 1 year of deposit, we have the following shown on screen. If the interest rate decreases but the interest is compounded more often, for example, the interest rate becomes 50% and the interest is compounded twice a year, i.e. r equals 50% equals 0.5, n equals 2, after 1 year of deposit, we have the following shown on screen. If the interest is compounded 4 times a year at a 25% interest rate, n equals 4, r equals 0.25, we have the following shown on screen. For 10 compounds a year at 10% interest, n equals 10, r equals 0.1, we have the following shown on screen. For 100 compounds a year at 1% interest, n equals 100, r equals 0.01, we have the following shown on screen. For 1,000 compounds a year at 0.1% interest, n equals 1,000, r equals 0.001, we have the following shown on screen. As you see, this is a converging series, and when the number of terms points to infinity, the value points towards a number that is slighter above 2.7. Later on, Euler discovered that the series, we have the following shown on screen, converges to the same point as well. Therefore, he was the first to realize that this is a special number which needs more attention. Euler used the letter E to denote this new constant. Now when reading the constant E, we immediately refer to it as Euler's number, as the letter E corresponds to the first letter of his surname. As said earlier, this is an irrational number written, we have the following shown on screen. Usually, we consider only the 4 digits after the decimal place when dealing with Euler's number. Hence, we have the following shown on screen. Another feature that makes Euler's number special is the fact that it is the only number for which the derivative and integral have the same value, a value that corresponds to the original number itself. Derivatives and integrals are concepts that we are going to explain later in this course. When Euler's number represents the base of an exponential expression, we often write exp, x, instead of x. Exp stands for exponential. To summarize, Euler's number is the base of an exponential function whose rate of growth is always proportionate to its present, actual, value. The exponential function e to the power of x always grows at a rate of e to the power of x minus a feature that is not true of other bases, and one that vastly simplifies the algebra surrounding exponents and logarithms. That is all for lesson 13.4.2. To continue this tutorial, please watch 13.4.3. Definition of natural logarithm. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.com.